Welcome back to physics. Today we are pondering total internal reflection. So let's introduce with an example. Light is traveling in water incident on air. So we have shown in the diagram below a flashlight below water shining from the water up towards a boundary with air, and we're considering different angles of incidence, and we want to know what the angle of refraction is. So then if we follow a ray of light from our flashlight up towards the boundary, in terms of the refraction, I'm going to draw the normal to the surface in. So perpendicular line to the surface. Think about what direction this light will bend. Your index of refraction for each substance, air is 1.000293. Water, the index of refraction is 1.333. So you're going into a lower index of refraction. That means that your light speeds up, and if your light speeds up, your light will bend away from the normal. So instead of following straight up along that line, I'm going to bend this light further away from the normal. So then our angles, theta I would be right there, theta R would be right here, measured from the normal out to those given rays. So then we want to calculate theta R value is for each of those theta I values. Well, our boundary is from water to air. So then everything on the left side deals with water, everything on the right side, air. Snell's law, N1 sine theta 1 equals N2 sine theta 2. Plugging in our values, that's a 1.333 sine 20 degrees equals a 1.000293 sine theta R. Dividing the 1.000293 to the other side, getting a decimal value and taking the sine inverse, we get a theta R value of 27.12 degrees, which is larger than the theta I value of 20 degrees, so it did indeed bend away from the normal. If we plug in the other angles, then what we find is for the 40-degree angle, we get a 58.94 degrees angle. So that it is bending even further away from the normal. When we plug in 50 degrees, we find that we can't get a value. If you try to plug in 50 degrees in your Snell's law equation, where the 20 degrees was up there, you will get down to an equation that is basically sine theta R is equal to 1.0208. Well, sine values don't exist greater than 1, so then your calculator is going to give you an error message. It's not telling you you did something wrong. It's telling you Snell's law doesn't apply. Snell's law doesn't apply because your light will not refract. Instead of refracting, basically what's happening is you're pushing the light so far away from the normal that you run out of space to push it any farther. If you consider this diagram, starting on the left side, you have the flashlight shining up at the water at a very small angle of incidence. Progressively, as you move across the diagram towards the right, each successive flashlight shines at a larger and larger angle of incidence, and the angle of refraction becomes larger and larger, bending away from the normal until that refracted ray travels all the way along the surface. That angle of incidence would be called the critical angle. At any angle greater than that, you see then the light doesn't even refract out of the substance, but instead reflects back into the water. Total internal reflection, which is the application that we're moving into. So then at that, and we're going to calculate a second, that large theta I value, you get a full 100% perfect reflection. Now, very important for this to happen, you have to be internal, which means your light must start in the substance that has the higher index of refraction. It must also be incident at a large enough angle. By this large enough angle, we're going to define what that angle is, the critical angle. So basically the critical angle is the theta I value where theta R is equal to 90 degrees. So for the previous boundary we just had, where we had water to air, and we had the light starting in the water, and we had then our theta I value here. If we wanted to calculate what that critical angle is, we would use Snell's law, going from water into air. We would be solving down for that angle of incidence, and for the angle of refraction, we would put in 90 degrees. So then the angle we solve down for, we will call the critical angle, and we get a value of 48.6 degrees. That's the critical angle for our boundary from air to water. So then what that means, well, we can have a theta I value that is less than 48.6 degrees, a theta I value that is equal to 48.6 degrees, a theta I value that is greater than 48.6 degrees. If our angle of incidence is less than 48.6 degrees, we get normal refraction that occurs. Snell's law applies. If it's equal, we still get refraction, but we get that maximum refraction so that theta R is 90 degrees. And if theta I is greater than 48.6 degrees, we get this total internal reflection. So then the critical angle is kind of the cutoff point. It is the end of refraction right before total internal reflection occurs. So each boundary, as long as you're starting internal, inside the substance that has a higher index of refraction, then above that critical angle, you will only get total internal reflection that will occur. Now let's demonstrate. Here I have an animation or a video that shows what happens as you change the angle of incidence. So as I gradually move the laser over, you can see how the refracted light is moving further and further away from the normal. Right there is where we cross the critical angle. Now we get total internal reflection. Now I'm going to bring it back all the way across the other way, and you can see how the light is refracting, and right there we cross the critical point again to get total internal reflection.
I'm going to try my best to be able to demonstrate total internal reflection. It's much better when you can actually see it live, but you should be able to make some observations from these demonstrations. Starting off with the aquarium. What I have, water in the aquarium, you can see it kind of moving around a little bit. Various and assorted toys back here behind. To be able to observe total internal reflection, you have to be internal. You have to have the point of view of being under the water. So what I'm going to do is I'm going to take a minute and lower the position of the iPad, shift the aquarium a little bit forward so that the iPad is below the aquarium level, so that you have the perspective of being underneath the water, and then I'm going to demonstrate a little bit more. Now, you are below table level now, looking upward at the water in the aquarium. Now, it's just clear water, but notice when you look upward at the water, you don't see, you can see my hand there through the air, but as soon as my hand goes here, you can't see my hand. Instead, what you see is a reflection of these toys that are laying on the table. So the light is coming from these, going upward towards the surface of the water, coming down and reflecting into your eyes. So that total internal reflection is 100%. It's a perfect reflection that you see when you have an angle greater than the critical angle. Now, to give you a little bit of perspective, I'm going to stick my fingers through the water. And notice what you see when my fingers are through the water. You can't see the rest of my hand, but you see my finger pointing downward, and then the reflection of my finger pointed upward. Total internal reflection.
So why, when you're underneath the water in a swimming pool and you look up towards the surface, can you not see that total internal reflection? Well, we have a few kids here underneath the water, and the first thing I want you to notice is how the surface of the water is moving around. That movement means your surface is at various different angles, so oftentimes that reflection is a little bit dispersed or hidden. Let's take a look at a few different pictures. Here's an image of a surface from underneath the water, and you have part of a boat there, but you notice where there's kind of a cutoff. I'm going to highlight a little bit. Right in this neighborhood and all the way across to the other side, there's a cutoff there. Well, that cutoff is your critical angle. So then light coming in from this region here, where you have the greenish color, that's actually being totally internally reflected off of the ground underneath the water in the distance. Above, where you have the blue sky, that's light coming in from above. So you have that cutoff between total internal reflection and light that is escaping or light that's coming in from the top. Now, it's still kind of not a perfect mirror reflection. So if we take a look at another picture, here we have two swimmers on the bottom, and you notice in this region right there, that color that you're looking at, it's the same color as the bottom of the pool right there. So light is coming in, the sunlight from the outside, hitting the bottom of the pool, reflecting off the bottom of the pool, shining onto the surface of the water and totally internally reflecting in the water. This light then goes into our eyes and we see the same color on the surface of the water that there is on the bottom of the pool. So you have, again, this kind of cutoff line right there between total internal reflection and then light coming in from the outside. If you could get the water to be perfectly stationary, then this is what it would look like. Looking at the top photograph there, you have total internal reflection. You have a very, very well-defined line there where light is incident at an angle greater than the critical angle. So you have a literal mirror image of the bottom of the pool. So then your actual pool, here is an actual wall of the pool, here is an actual wall of the pool, here is the actual bottom of the pool. And then you have a total internal reflection starting right about here and right about there and then back there in the middle. So everything above those green lines is a total internal reflection, and then right along this angle here, or line here, that's where your critical angle would be. The bottom photograph, this is a picture taken from underneath a swimmer, and again, you see this pretty well defined cutoff line. Now it makes a circle whereby light is coming in beyond the critical angle at a value above the critical angle, and you're getting total internal reflection on the outside. So if you're in a swimming pool or if you're at a pool and the water is still, very carefully slip into the side of the pool and go underwater and look up. When that water is still, you will be able to clearly see total internal reflection.
Now, I know you can't see what you're looking at. The room is dark and the aquarium full of water is in front of you. I'm going to shine a green laser through it. Hopefully you can see this green laser beam very, very faintly traveling through the water. I'm going to sprinkle some salt in so you can see that laser beam hopefully traveling through the water. Now it's traveling straight. I'm going to send it towards the surface of the water. And hopefully you can see it, and I'm sprinkling salt in. Totally internally reflecting off of the surface of the water. It is hitting at an angle greater than the critical angle, and in so doing, it is totally internally reflecting off of that surface.
I tried to set this video up in class, but it just was not visible. So we're going to take a look at this YouTube video. The girl is shining a laser through a 2-liter bottle full of water. She should be wearing safety goggles. There's a hole in the left side of the bottle, and in a second she's going to remove the tape here to let the water stream come out of the bottle, and we're going to see it totally internally reflect in this water stream.
It's definitely aimed towards the stream.
As zoomed in as it can get.
Now, in just a second, I'm going to turn the lights off again, and I'm going to show you light totally internally reflecting through various different things, but I want to show you the shapes that I'm going to show. Spiral, that is a solid fiber. A rectangular piece of, it's not glass, but it's a plastic material that has tiny little air bubbles in it. An actual glass fiber that is covered in black to be able to protect it. And then this is the cable that is used if you've ever had knee surgery, okay, anything arthroscopic, whereby they cut a few holes, say, in your knee, and they go in and they have surgery, they do surgery all based on fiber optics. This is one of the cables that they use in those surgeries. So, just so you know what we're looking at before I turn off the lights and you can't see the actual object. Now, let me turn off the lights. First of all, the spiral. If I shine light in the end of it, it totally internally reflects all the way around the spiral, hitting at an angle greater than the critical angle, and then comes out the end in the center of the spiral where you see the bright green dot. If it's not hitting the end, none of it is illuminated. If it is, it's just reflecting again and again and again off the sides. My personal favorite, the rectangle. When I shine light into it, the light is going across. Again, there are tiny air bubbles in here, and that's what allows you to be able to see the light. To get it to totally internally reflect, I have to rotate it. And when I rotate it, you can actually see the reflection inside the glass, and as I rotate it more, you see more and more reflections. Total internal reflection. The black fiber that is glass inside. I'm going to find both ends of it, and if I have enough hands, I'm going to point one end towards you, and I'm going to shine light into the other end. When I shine light into one end, you see that glare of light when I hit it right on. It's totally internally reflecting hundreds of times inside that glass fiber. Now, the cable used for arthroscopic surgery. I'm going to shine laser light into one end of it, and I'm going to point the other end towards you. The dimmer light to the side is where I'm shining it in. The bright light coming towards you is after it has traveled all the way through, totally internally reflecting. If I'm going to hold it up higher, if you can see now the cable itself, you can see all kinds of little bright spots. This is a retired cable. It's no longer good to be able to be used in surgeries, and they know it's no longer good because a bunch of the little glass fibers are broken. And so you have light that is escaping out of there, total internal reflection. So if you know anybody or you yourself have ever had like a knee surgery, an arthroscopic surgery, then what goes on is they cut a few holes in your knee. One of those is a hole for a cable to go in, light to go in, total internal reflection, reflecting off of whatever's inside your knee, back out, and then the doctor is able to see that on a screen. It's probably a hole for cutting tools, a hole for maybe suction, and everything is done remotely basically because you can use that total internal reflection and then other medical tools and things that are small. Now I have a few different toys that something like this, maybe you've seen things like this sold at Kings Island at the end of the day or at county fairs and things. Little flashlight, you turn it on and you get all these little dots of light coming out the ends of the fibers. Total internal reflection. Okay, I have a hat. I'll demonstrate this in just a second. And then a flower, but I'm going to turn the lights off to be able to talk about these more clearly. Now you can see the flower. Light is coming up from the base, totally internally reflecting in the fibers that form the stem and form the leaves. And then the light comes out at the tips at the ends of the fibers. There's a color filter that is rotating over the light bulb. And so you see the variation in color. Then my hat, if I put it on, I've got my hat here, and it is totally internally reflecting light from the band up through the fibers, and you get that different illumination pattern. I can change the pattern once I find the button. Total internal reflection.
So let's recap with one example. Light is traveling across a boundary between air and crown glass. In which substance does the light start for total internal reflection to occur? Well, remember that it is internal, which means your light has to start in the substance that has the higher index of refraction. So checking our index of refraction values here, our boundary goes between air and crown glass. Crown glass will have the higher index of refraction, so then the light must start in that crown glass. Now, part B, calculate the critical angle. We're going to calculate the critical angle, so we have light here at our boundary where we have crown and we have air, and our light is starting out down in that bottom substance, and we want to calculate what that critical angle is, which would be that angle of incidence. So we'll call it theta C instead of theta I. We're going to use Snell's law. Remember, when you're using Snell's law, specify your substances. First substance, crown glass. Second substance, air. So then Snell's law, N1 sine theta 1 equals N2 sine theta 2. When you plug plugging all the values like we have before, but then when you get to the angle of refraction, remember at the critical angle, that angle of refraction is 90 degrees, so we have to plug in a 90 degrees there. Solving down, we get sine theta c equals 0.658. Don't remember, you have to then take a sine inverse to be able to find that angle. And then we get the critical angle for glass. Crown glass is 41.15 degrees. In terms of interpreting that, well, we could have light traveling at less than 41.15 degrees, and then that light is just going to refract normally out into the air. When that light is incident at exactly 41.515 degrees, then it will also refract, but theta r will be that 90 degrees. And then when you are above that critical angle at 41.15 degrees, that light will totally internally reflect, and it will stay in the crown glass. Ponder physics.